The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So looking at things here, right? X and theta and how they can be represented. But you can create some really beautiful images out of that. You can even create some of my slides. You can create some really interesting pictures like this. So if I this picture is made in that x theta space. The coordinates are a little bit changed here. This is a slide from Sam Hasinoff, and there's a robot that Andrew Adams built at Stanford, just using Legos. And you can do this for your assignment as well. You can build a Lego-based gantry that can, shift and take these pictures. For your assignment, you're just doing 1D translation, but you could even do 2D translation. And then imagine if I put a camera here and I simply translate it. And now we're in flatland. When the camera is here, I will take a picture and put it over here, this line. Okay. Then I'll move the camera and I'll stack those images. Right? So for example, when I am so yeah, if you look at this particular green object over here, you'll see that it creates actually a line. Because when I start translating it, it creates that line. On the other hand, this particular white sphere ends up mapping to this really strange object here. So this is the visualization of the same space that you saw earlier, which looks, maybe simple and very boring. Okay. So once you start putting interesting objects, that's how your light field starts looking. And this is basically a light field. Here is T and theta, but it's same as X and theta. And the appearance of this room through this window, all you're allowed to do is look at this world through this window. You cannot go inside. You only see from outside. Everything that can be captured about this scene through this window is represented in this 2D light field. Okay. So now if I want to create any refocusing effects, any depth of field effects, all the information is available here. And if I just reuse the pixels from here and take projections and so on, I can create the effects. You're going to twist your mind around it, and then it starts making sense. For those of you who have a computer vision background, this is also known as epipolar plane images, or EPI. Okay. So let's go back to some of this concept we were talking about earlier, where you're going to represent each part of the lens as a different camera. So 5 subsections, 5 cameras. Except we know that if I want to focus at infinity, I can just take the sum of all these images and I'm done. Right? Or average of those images. But if I want to focus closer, then I cannot just take the average. I have to shift and add. Okay? And what this prism is doing in the real world is doing the shifting for you. Okay? So let's go back to this example of this notion of shifting and add. So I'm going to compare this with the 5 camera situation. See if I have a point here. From the first camera, the image goes here. The second one, it goes there. Third one, it goes there. Fourth one goes here. Fifth one goes here. And that's my pinhole camera here. So So as you can see, if the point is close by, the coordinates here are not the same. Here it's near the 0, and here it's a little further up from the center, and here it's further down. It's down from the center, and so on. So when I have to bring these 5 images, I need to shift these images so that these all guys overlap on top of each other, so that this point will be in sharp focus. The lens does that for you automatically, because of the prism. If I put a painting here, okay, and there is just a pinhole here, this is A, B, C, right? This will come back as A, B, C. Okay, but this one here would have created an image that looks like this. But because of the prism, it rotates the image, and then this thing shifts down. So they are on top of each other. And because of this part of the prism, it shifts. The image would have been created here, the ABC, but shifts just a little bit, and so on. And for the other one, the image would have been formed here, it shifts up. So the prism does the job for you, basically, of shifting these images. So that's a very simple way of thinking about how we can emulate a very large lens by an array of cameras. So the top cameras here should shift down in their images, and the bottom cameras should shift up. And by doing that, you can focus anywhere you want. Except that in case of a traditional lens, once the photo is taken, you're done. In case of an array of cameras, you can take those pictures and shift as much as you want and add them in interesting ways. And that's why Lightfields are so powerful. So instead of using now an array of cameras, we're going to build lenslet arrays or some other fancy optics so that I can directly capture these 5 images in a single snapshot. Okay. There are basically 3 ways of creating. Yes.
So that these for all these cameras would be the optimum that the aperture is small.
So this is just conceptual. Yeah, you're right. So when you think about the Stanford camera, you want each of these cameras to have infinite depth of field. So everything is in sharp focus, which means it's a pinhole camera. So conceptually, yes, it's a pinhole camera, but in the real world, you cannot have a pinhole camera. So
you still try to keep the aperture.
They try to keep the aperture small. But if you use a really cheap camera, like a cell phone camera, they usually have a pretty large depth of field anyway. So they're as close to pinhole as you can get. Okay. So basically 3 ways of capturing light field. Something that exploits shadows and pinhole array, 1908. Something that uses lenslet array, also early 1900s, and so-called heterodyning after 100 years in my group. Okay. So it took 100 years to come up with a third solution. Think about how you can, as I said, a subaperture is basically a pinhole with a prism. Right? So I can take each of these pinholes and so you have this, and a third one would be, I can just put a pinhole, and in front of this, I can put a prism. In front of this, I'll put a shallower prism. In front of this, I'll just put a piece of glass. Here, I'll put right? So lens is basically an array of pinholes with a set of prisms. And as we saw, if you have 2 corners of these pinholes, the image will be formed with a large sensor, but the lens does a smart job of just bending light at this prism and this prism to bring it in sharp focus. Okay. So this figure is from Lippmann, I believe in 1930. Sorry, this one is Lippmann, this one is Ives in 1933. And he said, okay, if you really want to capture each of these rays individually, you can just put a pinhole array. Okay. So maybe it's on the next one. Okay. So if I put a pinhole array there and take a picture, so no lenslet array, just a pinhole array, then you end up getting a picture that looks like this. Okay? And if you zoom in on that, you'll see that under each pinhole, it will create a disk. So remember we had a lens slit, and we had a lens slit here. Instead of that, which is going to happen. And then when Rolf was explaining this, you use a pinhole adder, right? Yeah. So that's an example of this pinhole. So this is our solution number 1. This is our solution number 2, and solution number 3 we'll see in a second. And it turns out, if you think about a glare in a scene, like a lens flare, a 2D image might look like that on the top right. But if you zoom in, it turns out in the 4D space, the glare manifests itself as this bright spots in a corner of an image. So you can just go through this image and eliminate all the bright spots, and you can get rid of lens flare. And so you can remove the outliers, just do some kind of a median filtering in a neighborhood, and the lens flare is removed. All right. So the second way of doing it is by using lens slit array, which we already saw. So I won't repeat that again. And now comes the question of what happens to points that are in focus versus out of focus. Okay? And this is a very key concept you have to understand. So let's say I have a lens slit array. And I have a point that's in sharp focus at one of these lenses. And the same situation here. If the point is in sharp focus at this pinhole, okay, light will go back and I will create a disk here. But let's say this is the red crayon. All the rays are red. And when they come back to this pinhole, this whole thing looks red. So that's why in this part of the image, where in the original photo, with the original camera, the red crayons are in sharp focus, the whole disk is red. Okay? Which means that every part of the lens is getting a red ray as input from this point. But let's go to a part that's actually out of focus. Okay? So I believe this one is over here. So that's on the boundary between maybe a yellow crayon and a blue crayon. So even in the original photo, it's out of focus. If you didn't have a lens slit array, it would be out of focus. And here you can see part of each blob under a lens slit is yellow, and the other part is blue. How's that happen? So we have a situation where we have a autofocus. We have a yellow and blue, yellow and blue. Okay. But they're actually out of focus. So if I start shooting the rays from that, and there's this one, this is fine. If I just take the one from the yellow-blue boundary, okay, for this part, the light is in focus closer. Okay, it's in focus closer, and the image is actually out of focus. Okay. So for the bottom part here, all these rays are going to be in. Okay. But this part here is not here. And from the blue part, again, we shoot the rays. And what you will realize is that if you look at this pinhole, we've had a yellow cone coming through and a slightly offset blue cone coming through. And because they were not in sharp focus, they will contribute through one pinhole so that part of it is yellow, part of the blob is yellow, and part of the blob is. Now, let's go in the. This one is the further. Let's go to the one that's further away. It's too bad the image is not very far. Alright, let's look at this one. This one is a better example. So if you just look at the green and the one that's kind of blackish next to it. So this one was very easy. The blue was to the left of the yellow in the original picture, and even inside each blob, the blue is to the left of the yellow. But if you see this one, the green is to the left of the dark region, so it has flipped. So here the left-right ordering is maintained, here the left-right ordering is switched. And can anybody tell me what's going on here?
It's behind the focus.
Exactly. If you're in front of the focus plane, the left-right remains in the same position. When you're behind the focus plane, the order is switched. Okay. And that's why you cannot simply take this image and reconstruct the original high resolution image. You have to do a lot of processing for this to be able to recover. So it's a lot of fun to look at these images. There's all this information that's encoded, the four-dimensional information. Okay. So here is our solution. Instead of placing a lenslet array, we're going to place a mask. Not a pinhole array, but a specially printed mask. You can just take a medium format camera, such as a Mamiya, just remove the IR protective glass, and then simply drop a film on top of the medium format camera sensor. Put back the protective glass, and you're ready to go. And you have a light-field camera. Okay. So in this case, we are not putting a pinhole array, but so I'm going to go through these slides very quickly. Instead of putting a pinhole array, we're going to place a different type of mask to capture that. And a few concepts that we have to look at before we get there is that there is this concept of conjugate plane. That if a plane is in sharp focus at a sensor, then this plane and the corresponding sensor plane are conjugate with each other. If I put the object closer, then I must move the sensor further back. And those two are conjugate with respect to each other. And that is defined by the lens equation. 1/f equals 1/u plus 1/v. Okay? Now the key concept here is that a lens copies a light field from the outside world to the inside world. Okay? What does that mean? If I have, so originally what we were doing, we were assigning some coordinate system. We called it the theta plane, and we call this one the x plane. Okay? This is our two-plane parameterization. Now there's a little bit of fudging going around here because theta here doesn't really correspond to absolute angle, but a coordinate on this axis. So theta is 0 here, and let's say it's plus 5 here and minus 5 here. Okay. And x is of course goes from 0 to 1000. And this is our light field. The relationship between any point here and any point here defines the 2D light field in class. Now it turns out, let's say I have 2 points here, A and B, and I have 2 points here, A and B. So A and B has to be always opposite. Okay? The image is locked here. I can also assign a new plane here. I think I call it x prime. Or just x for simplicity. This light field, which means this x theta relationship, is maintained in this theta x relationship. So if I take a ray here from, I'm going to assign this also, let's say I put a painting here. Okay? And I assign the coordinate of 1 to 1000. And here I assign a coordinate of 1 to 1000. It's good to take some real numbers. Then if I shoot a ray from, 200 to plus 4, right? I can guarantee, if the plane was in conjugate, that the 4 will map back to, sorry, A to B was switched here. This is A. It will map to the pixel as 200. Okay. And of course, if I have 200 mapping to 3 here, 3 will automatically map it to also 200. And that's only because this painting is in sharp focus at a sensor. This notion of conjugation means that the light field of this x theta coordinate is mapped to this theta x coordinates. So I can take parameterization, I can shoot all the rays here. If there's a point here and I shoot rays out, the same point will be in sharp focus here and all the rays will converge. Okay? If I have two rays that are starting in the same theta direction, they'll come out here in the same theta direction. Okay, and so on. So basically I'm creating an exact replica of a light field here inside. And this is possible only when the lens is extremely good quality. So it might do a pretty good job, a not so good lens will do a good job of copying it in the center but not at the edges, or it might do it for one wavelength but not for others, and so on. Right. And this notion of copying the light field makes the lens very unique, because we know that the appearance of the world is 4D. It completely describes the appearance of the world, and what the lens has done is optically it has copied the appearance of the world faithfully to something that's inside. Okay? And now we just need a good quality sensor to basically take the hologram of what's out there. And I'm using the word hologram to indicate the 4D appearance of the window into the world. Okay. So this window that we have here is exactly copied over here. So anything that's behind this window is faithfully reproduced over here. Okay. Unfortunately, in a traditional camera, you take that window and you just map it back to a 2D image. So the problem is the sensor. The optics is doing its job of going from 4D to 4D. So 4D in, right, and 4D out. But the sensor does a terrible job of maintaining that 4D just gives you 2D. But if you have these three solutions, you can recover this 4D representation. Okay. So let me just explain this concept one more time of how the rays, when they're in sharp focus versus out of focus, look differently. And I promise you that after you understand this concept of rays and ray space and all that, everything else, out of focus and depth of field will become extremely easy to understand. Okay, so just see how this works out. So now let's say we have a point here. Okay, we can either represent the light field here, or we can represent it here. It doesn't really matter. Now here what we have is a point that's emitting light in all directions. So how does the light field look like? There's a point X and it's emitting light in all theta directions. Okay. Now we know that the lens is going to make an exact replica of that inside. So when I come here, I have a particular X and light is coming from all different directions. So what's coming at the plane is exactly that. Okay. From this, how do I form an image? How do I realize that if I integrate the radiance along each of these rays, I will get the intensity at this space? We are going from a 2D world now to a 1D world. In the general case, we go from a 4D world to a 2D sensor. 4D representation, 2D sensor. Here we have 2D light field and 1D sensor. How would you do it? Sum over theta. I'm just going to sum up everything that comes out of theta. And then I'm going to take all these values and sum them up. And mathematically, that's just taking a projection. I'm just going to take this 2D world and flatten it to a 1D world. Okay? Or you can call it line integral. So imagine I had all this tennis balls here, and I just dropped all of them under the force of gravity. The number of balls I will count here will be the intensity of that pixel, and it will black everywhere else. Very simple, very clean. Now what happens when something is out of focus? Okay? If it's out of focus, then the lens is doing a good job of transferring the 4D here, 4D here. But it did the right job for this plane, not for this plane. Okay. So how do we represent the new space of light field? Again, this case the light field is very simple. There's just one point light. We have this bunch of rays and we want to represent that. Previously, the light was reaching only one x point. Now it's reaching an array of x points. And for each of the x points, there's only one direction in which lights are acting. Okay? So there's still a line. That's the axis missing. Okay. So I have a bunch of different points here. And for each of them, there's a direction along which the lights are acting. So this is the notion of shear. We had a straight line, we sheared it a little bit. And now, how do we compute the light? How do we compute the intensity from the set of rays? Again, the same operation of, imagine we had all this tennis balls here, and we're going to let them drop. Okay. If you let them drop, we're going to get intensity that goes over a set of pixels rather than just one pixel. Right? And that's the captured photo you'll see. When something is out of focus, you don't see a sharp point, but you see a blurred set of values. So again, we start from here, exact copy. For a given x, we have all the thetas. We project, we get a sharp point. That's the intensity of the captured photo. If it's out of focus, the set of rays can be represented on a slanted line now. When we project that, we get the integral, and that will be blurred. Is this clear? So now when you're thinking about doing an assignment and you have a set of photos and you want to do refocusing, okay, you can think of it in multiple ways. If I stack all the photos, okay, so remember, taking a picture with array of cameras is the same thing. So I'm going to put an array of cameras here. And the coordinate of the camera is theta, and the framework of the camera is x. So I can take a picture of the first camera, and I'll put that as the top row of this. I'll take a picture with the theta equals 2, I'll put it over here. Sorry, theta equals 5 over here, 4, 3, 2, 1, 0. If I have 9 cameras, I'll put them over here. And if I just want to take a picture that's focused at infinity, I'm going to stack all those pictures and just take the sum along vertical direction. And that will focus at infinity. Right? If I want to focus closer, then I shouldn't just sum them up as they are, but I need to slightly shear them. So I'm going to keep the center camera image as is. I'll take the theta equals 1 camera and shift it to the left by 1 pixel. I'll take theta equals 2, I'll shift it by 2 pixels, 3 pixels, and 5 pixels. minus 1, minus 2, minus 3. And the 1 over here, I'll shift by plus 1, plus 2, plus 3. And if I sum them up, I'll be actually focusing on a different plane. So this is the main concept behind refocusing, that it's shifting and adding. And you can think of that within a single lens, or you can think of that using array of cameras. Clear so far? So next time you're taking a picture, think about how much work the lens is doing. It's copying the light field, right? It's capturing the hologram of what's out there, right? This is using the popular terminology. It's capturing the hologram of what's out there. It's recreating that hologram very close to the sensor, and all that the sensor is doing is just recording that as a 2D image finally, because the sensor doesn't have an ability to record in a traditional sense a 4D hologram. It can always sense a 2D image, and it's doing all of that at the speed of light. Isn't it great? And that's why computational photography is exciting, because there's some work you can let the computer do, and there's a lot of work you can just let the physics do for you. But when the physics does it for you, it happens at the speed of light with almost no additional cost. So doing this co-design of the physical device and the computational device brings in the real power in computational camp, computational photography. All right. So let me switch to some other things I wanted to show you. By the way, is this all clear so far? This part here? This will be on your exam, remember. Yeah, this is the fun part. All right. So now that we have understood all these concepts of rays and 4D space, let's see how it impacts. We already saw autofocus, but let's see how it impacts some other elements of photography. So let's say you have a point light. You take the photo in sharp focus. It looks like a point. If you take that photo out of focus, it appears as a disk. Right? And if you saw this resolution chart, then it was blurred as well. Right? And here's an example to answer Dina's question, where we started with a 2D image, and now we have another 2D image, but the blur, the image was convolved effectively by this disk. So we took every point, placed a disk around it, summed up all those values, and assigned it over there. Okay? And which was achieved using the same effect as this. Right? Every pixel in the world, like this one here, actually is contributing to a disk. Okay? The other way to think about this is if I just take one pixel here and go up vertically, it's coming from different points in the world. Okay? And that's how we can specify blur. So now we have that. I'll come back to this later. But every once in a while we can create some really interesting, and this is called bokeh in Japanese, or bokeh. What's the right way to say it? Masa?
In Japanese?
Yeah.
Bokeh.
Bokeh.
Yeah.
All right, good. And the exploitation of out of focus blur. But sometimes you can do some interesting things. Instead of keeping the aperture completely open, you can insert a special pattern. Okay? So we're going to place this crossword puzzle shaped mask in the aperture. And now if I take the photo out of focus, instead of getting a disk, the LED that you saw earlier, out of focus will appear something like this. The same 7x7 pattern that you have here ends up appearing over here. You see these two lines, and this whole pattern is exactly different. Okay, so you can do some really interesting things with it. So again, photographers want to take pictures that have really beautiful bokeh. So when it's really tiny aperture, things are in focus over large depth of field, but with a very large aperture, the background is completely out of focus. All right, good. So now you can start playing some really interesting tricks. Okay? You can take a scene which has these tiny bright spots on a specular reflection. And in your aperture, you can, instead of putting the 7x7 crossword puzzle shaped mask, you can start putting some alphanumeric characters. Okay, so I'm going to take 7 different pictures. One with this aperture, one with this aperture, one with this aperture. Okay? And if you just take an addition of those 3 photos, so when you take a picture with this aperture, you get a vertical line for every bright spot out of focus. For this one, you get horizontal line, vertical line at a different position. If you just sum them up, every out of focus spot will have a letter 7 on it. So you can, I believe there's an animation here. So you can see letter 8 appearing at all different places. Okay. So let's try to understand what's going on here. So that's with a disk aperture, like a traditional aperture. This is the one with some special aperture. Okay. And if you want, you can even say, "Happy birthday, Jennifer," and it'll just show up there. So if you take a picture of all the candles, every candle will say, "Happy birthday." Okay. So how is this taking place? It's difficult to explain purely as autofocus blur. But if you think about what's going on over here, it's very clear. So we have our lens, and we have our sensor. We have one candle or one bright spot. If it is autofocus, it will create a disk here, right? But imagine you started putting some interesting character. For simplicity, I'm just going to make a 1010 pattern. So I'm going to put a film here that's open, closed, open, closed. Okay. So in this part of the lens, light will go through. So I'll get some value here. This part of the lens, light is blocked. So I don't get anything here. Over here, light goes through. So I get here, and this part of the lens is blocked. The pattern I will get here will be also single. That will be blur. And if I put a different pattern here, I will get a different blur. And that's how you can put a code in the aperture. How would you think about this in the x theta space? Okay. But remember, the world is not as simple. There is not just a point, but there are a whole bunch of things going on here. And all of them are interacting at the same time. If you go to the x theta space, what we have is we have the x space here, the theta space here, and by blocking this part and this part, what I'm saying is that the top is fine, I have blocked this part here. This is deleted basically. And this part is open, so that's fine. And then again the bottom part is deleted. So what the optical system is doing here is taking the light from outside and it's just deleting all the rays here. It's just blocking all the rays. And then when you take a picture, you can create any effect you want. That's the basic concept. And then again you can play this cheesy trick of taking multiple images with different blur, and because of linearity, which we discussed last time, of light, you can just take the addition of two images to create an illusion that the aperture actually had those three apertures. So instead of putting a 7 in the aperture and taking one picture, you can take 3 pictures with each of those different apertures and just take the sum of that. And that's the beauty of light and interaction of light at normal intensities. You can first take a picture and then take an addition, as opposed to adding it in the physical domain and then taking a picture. This is good. So it's a fun project. If somebody wants to try it out, create a nice bouquet, beautiful patterns. You can also put an LCD in the aperture, so it's not just a film, and you can change the LCD so that depending on the event, you can change the different pattern, and you'll get very interesting effects of autofocus. Okay, so what's going on with animal eyes? And we'll have a full lecture a little bit later on animal eyes. And compound eyes of animals are also very interesting. These are basically array of lenses, okay? But just hundreds and hundreds of them. And this is kind of an artistic rendering of what the creature must be seeing. Just an array of very tiny images, which is not true, as we will see later. But that's how the rendition looks like. So there are projects such as Tombow, which tries to mimic this concept to basically reduce the thickness of your camera. Okay? So if you have a 35mm lens, it will be about 35mm deep. But imagine if you want to create a camera that's really, really thin. One way of thinking about that is I can just split my lens into a set of tiny lenses. Okay. So if you go back to this diagram over here, I have a sensor and lens slit and a main lens, I'll just get rid of this main lens. All I have is this. And the question is, can you do something useful with that? Any guesses what you can do, what you cannot do? That's the situation. So there is no main lens out here. Every point in the world maps to every block. Just got rid of block transformation. So if you have 50 such lenses, every point will be seen 50 times. Okay, but each of the images is actually pretty low resolution.
Isn't this basically the same as the light field big rig?
I'll repeat that.
Isn't this basically the same setup as the light field big rig but smaller?
Big rig?
The camera rig.
Yes. Okay, so that's a good point, right?
Yeah.
So let's say I tell you that you have a 16 megapixel sensor. Okay, you have 16 megapixel. In flatland, you have 4,000 pixels. And you can use the 4,000 pixels any way you want. Okay? And you have some resolution in theta, some resolution in x. And if I don't use the Lightfield camera, I have 4,000 pixels. If I place a light field, and let's say under each lens I get 10 pixels here, I'm subdividing my lens into 10 zones, right? And my actual resolution is only 400. So I have lens slits going from 1 to 400, and under each lens slit I have a pixel I have 10 pixels. So in that sense, my resolution in x is 400, and resolution in theta is 10. And you can see that in the x theta space, it's this way. So this is only 10, and this is 400. Right? And inside this, I have 4,000 samples. Okay, because I have only 4,000 measurements, and I need to distribute them somehow. In a typical sensor, all of them will go exactly for one. There is no theta resolution, so I will have 4,000 pixels, but no resolution in theta. In a Lightfield camera, I could have 400 pixels and theta resolution of 10. Right? Or I could go in other directions where maybe this is even thicker and more theta. I could do, for example, 200 by 20. 200 by 20. How far can I keep going? So I started with something really thin, it's fat, it's getting fatter, but the total number of samples remains the same. If I get rid of this main lens, I'll give you a hint. What you end up getting is the opposite. You get 400 in theta and only 10 in x. So you have flipped from this condition, this situation to this situation. Okay, because now what you have is, if I have a world out here, x, then from every point, I can resolve this theta to 400 different lenses. So this one is gone. I can measure light coming out of this point in 400 different directions. Okay. But under each, I only have 10 pixels. So this is what I got you. So the key lesson here is that a lens, and without a lens, you are basically flipping the resolution in x and theta. If you have a lens, you get more spatial resolution but a little bit angular resolution, which is an ideal case. The world doesn't change that much if you change the viewpoint a little bit. But in certain case scenarios, as we'll see later in microscopy and so on, this is the other way around. So lens flips the resolution of x.
What I think is interesting is it depends on objects. So that holds at the time of day. But if the object moves really close to the one,
Yes.
getting a higher spatial resolution.
Exactly.
So it's this rotation as the object gets closer.
That's a great point. Did you hear that? I'll just draw it here, what you were saying. So if my point is very far away, right, I don't need to sample this point in 4,000 different directions, 400 different directions. I can take a sample and in 10 different directions, I'm fine. And then having a lens over here. Okay? But what Roth is saying is, now I can start coming closer. So bring the object very close now. Okay? Those 400 directions are sufficiently wide, spanning more angles. And it's become really, really close, right? And it's almost 1:1 here. Then I really want to see all these directions and capture them. So, and then the analogy of what happens when you go from here to here is that, remember, the lens is trying to do a very good job of mapping a 4D light field for the real world into a 4D light field on the inside world, inside the camera. And again, you can have a hologram analogy if you like. But when you don't have a lens, that's not true anymore. You have a light field here, and you have a similar light field here for this plane. Like, so imagine you put a hologram here. And the hologram has exactly 10 directions. So it's a 400 pixel hologram, it has exactly 10 directions. If I want to capture that, I should probably have a lens here. But if I have a hologram where I have only 10 pixels and it has 400 different directions, I'm so close to it, then it makes sense to get rid of the lens. So in microscopy and so on, So Mark Lovato has done some work in light fields in microscopes. He uses different configurations depending on the work. And the example that we saw for Schacht-Hartmann sensor for looking at the aberration of a point light, they didn't use the main lens either. They're expecting to see a point that's very, very far away. But they're not interested in taking an image of the point with this setup. They're just interested in finding the aberration. Right? So if you have a point very far away and the waves are coming straight, I don't need a main lens. If it's coming straight, all the images are at the center. And if there's an aberration, the sharp images are offset. So there are many configurations when you can decide between a main lens. And one thought experiment for you would be, what happens if there is more than one lens element or more than one lens element? So you should look up something called the Bohr super lens. It's a very fun concept where you actually have to put two lenslets next to each other. So it turns out by putting two lenslets right next to each other with the right gap between them, you can create one big lens. And it has very interesting properties because the focal length of that lens is dependent on the depth. In a traditional lens, it copies the light field from inside, outside to inside. But for a Bohr super lens, it does a very strange transformation of the incoming light field to outgoing. And once you start thinking about the world as not just 2D but 4D, and a photograph having not just a position coordinate but also an angle coordinate, you realize there are lots of other examples where this 4D representation starts making sense. So near the end of the semester, we'll be studying medical imaging and scientific imaging using tomography and deconvolution and so on. And all those concepts, CAT scan machine, they all work on this principle of being sensitive to position as well as angle. So in case of a CAT scan machine, you basically have you have some kind of a cylinder and the patient goes in here, right? The very first class we saw how this behaves like a jet engine, and you're sticking your head into the jet engine, But what is it doing exactly? It has a set of detectors and an emitter, and your head is in here. You turn on this X-ray source, and you take this image, take the shadows. Then you move this light source, and you take new shadows. And this is basically capturing the light field of your body using X-rays. To simplify this diagram, imagine this is flat. And in case of X-rays, the source is moving and the sensors are moving as well in a world. But to simplify this diagram, imagine I flatten this set of pixels and I put the lights at different positions, and you still have your head. I'm going to cast a shadow from here to here, and this is basically your theta coordinate, and this is your x coordinate. And every ray here can be represented in the x theta space. And then it turns out that if there is redundancy in your space, such as if you have a voxel inside your body, and independent of which direction the X-ray comes in, it attenuates with the same factor. So whether it's bone or muscle or blood, then although your light field is four-dimensional, the inherent data is only 2 or 3 dimensional. And so you can invert that and recover the opacity of each voxel. So the same thing can be done with light field. If you capture this 4-dimensional light field, now you can go back and estimate the depth of every point in the scene. So typically you use a stereo pair, there's 2 cameras, and try to do some correlation to estimate correspondence, and by triangulation estimate that. But in your second assignment, what you're going to do is capture the light field and directly from the light field estimate that. And the way you're going to do that is you'll basically again line up those images. If the point is in sharp focus, in the digital refocusing, all these values here will look the same. It's axis theta. Okay. But if something is out of focus, you'll need to all shift and add. Right? So you'll have to shear it at some point. And then all these values will become the same. And the fact that all the values are the same indicates that now you have achieved a digital refocus. Yes.
How can we achieve nonlinear focus? Like focus in a vacant set.
Yes, so that's a great point. So think about you have a point which is at different depth, and you're saying that in flatland, at the top of the image it shouldn't focus here, in the middle of the image it shouldn't focus here, and so on. Right? So this is my plane of or surface of focus rather than this. So all you have to do is for the top point, right? You have to keep. There's a little bit more you have to do, but I'll give you a very, very high level flavor of how you should do this. For this point, for this, you have the lens here. For this particular direction, multiple cameras. Right? For this particular direction, you can just calibrate your world. You can put a box, 1 meter wide, and I can say within this box, at the top left, I want the focus to be in the top left, in the middle, in the back of the frame, and the front. Right? You can just calibrate that physically. And you can move the camera and say that all the rays that go here, I'm going to add up and I'm going to assign value. But for the next pixel, I'm not going to add up all those rays, I'm going to add up some other rays. Okay. How do we achieve that in the x theta space? We know that for a point here, there will be some value over here. But for a point here, there will be some kind of a slope. Okay. So, if I just wanted to create an image that's So let's take something very concrete. If I have to focus on infinity, I know I should just project it straight down. I just sum up everything along vertical lines. If I want to focus somewhere closer, I need to shear this space. So I'm going to take this, and keep the image same space like that, and I'm going to sum up these values. Okay, and store the value. I'm going to sum up these values and store the value. And this means I'm focusing at this plane. If you want to focus at a slightly different plane, then is vertical, is slanted, but to focus at some other plane, there's a less slant in focusing. So now your question is, how can I do it differently for different pixels? So on the edges, I will just do vertical projection. Right? In the middle, I will do a slanted projection. And for all the places in between, I will do less slanted. And then I'll come back to vertical. If I do that, you will get a U-shaped pose. And you can imagine all crazy tricks you can do here. So one part of your assignment, you're going to look at, you're going to have a see-through. Okay? And for that, what I recommend you to do is take your array of cameras and then create some kind of a fence here. Okay, so in real world, I'm guessing there's some kind of a fence. It is a see-through part, and then there is some book or some painting back here. And you're going to take 16 images, and this is red, and this is green. You'll be able to get it off this way. Purely by focusing on the background. So when you focus on the foreground, you have to maybe shift by 3 pixels, and shift on the background, you have to shift by 2 pixels. But as an extra credit, what you can do is not just refocus, but also do some analysis of when you shift and add those pixels, if all those pixels have the same value or not. Okay. So if the red object wasn't there and you just focus on the green, all the pixels here will be green. All these values will be green. Yeah. But if you have some object here, some of these pixels will be red. Yes?
What is the y?
Here, this is x and this is theta. So theta is the camera number, and x is just the camera x. Yeah. So the image from the first camera is placed here. The image from the second camera goes here. And so on. Okay. And because you're doing this problem only in 1D, every row is independent. So think of this as only the center row of each of the 16 cameras. Okay, so going back to this example of red versus green, when you try to sample it, you'll see that you can refocus on green and the object will look mostly green, but there will be some reds. But then you can do very simple outlier rejection. And let's say you have 16 cameras and only 4 of them, so 12 of those are green and only 4 of those are red. You don't have to sum all 16. You can say, what's the color that's in majority? And that color is green. So you will not get a reddish tinge to your photo, but you'll get all the red altogether. It's not a simple linear projection. It's not just the sum of the pixels, but you're going to throw out colors that are in minority. And that way you'll get much better results. And again, this is in the second sub-part of this assignment. If you don't have to do it, that's fine. The main concept you want to learn is to shift. When you're taking the pictures, I have plenty of instructions in the assignment. When you're taking the pictures, make sure they are placed at equal distances, and you move the camera in a parallel fashion. Make sure the scene has vibrant colors. So this color should be sufficiently different from what's behind it, so that your results are easy to verify. And before you do any of this, use the data set I gave you, the test data set. And just take 100 by 100 pixel region of that and just run your code to make sure everything is run. And then you can go and take your own images. So even before you take the images, run your code on those databases. Because if you start with your own images and you're not getting the right results, you don't know if the problem is with your photos or with your code. Does Photoshop allow you to shift and map?
I haven't tried that. It's free to do it. You can put like, you can just do a whole bunch of layers with a little opacity and that starts nudging.
Well, then you write a script in.
Go figure.
Yeah, screw it.
Okay, but you can use HDR shop and do the same thing, and you can just shift because you can enter numbers, shift right, and you can also add. So you can do that as well. But of course, I recommend doing this programmatically because in MATLAB, this is maybe 5.5 line of code. Read images, shift, add. But just because it's 5.5 lines of code, don't wait till Thursday or whenever it is. Start today because the fun part of this is actually taking these images and creating scenarios where you can see through. And they should go on the Flickr page, and we'll comment on each other's work. For the first assignment, only about 5 out of several dozen submissions were on Flickr. So make sure the first assignment was all about getting your pipeline up and running. So almost everybody got an A, so you should feel good about yourself. But somebody got A plus, and others got an A. So I think you got an A plus. Good job. So yeah, make sure it's on Flickr and all those 3 places. And feel free to send me email. You can talk to Professor Oliveira or Professor Mukaigawa about any of this, or also Ankit. And Kimo is also here if you want to talk about 3D scanning and so on. And use the forum on the Stellar website and so on. So today's lecture was very much focusing on the theory behind how we start thinking. And then starting next week, we'll be looking at very different applications and different tricks we use in optics. So just go through the slides I posted today. They're conceptual, but it will take you some time to just grasp it. And again, as I said, it might feel somewhat odd to think in a dual space of x and theta, as opposed to just drawing the rays directly. But as you will see later, especially in your projects and so on, this will greatly simplify. This will greatly simplify the way you think about your problems. Cool. Have a good weekend.